Okay, I put this recording. Okay, fine, fine. So in previous class, we have been discussing for last two classes. We have been discussing about crystal structure and previous lattices, and then basically we started with the crystalline, polycrystalline, and amorphous structures, and then we try to understand the crystal structures, Bivas lattices, 14 Bivas lattices. After that, we try to understand Miller indices, and then we try to understand the what's closed back structures, FCC and HCP structures, and then we try to understand some common material crystals, diamond crystal and other things. Then afterwards we discussed what is called packing fraction and those things. Then we have done one or two problems in calculating what is the angle between given planes of the crystal, and also how to indicate the planes of the crystal in terms of HKL parameters, that is Miller indices. So these are the things we did. Now we have to go into somewhat what is meant by nano, what it is, and other things. Okay, that we discuss now. Let me share. Okay, so so what is okay? I hope all of you are able to see. Please respond. At least one person, please respond. You are able to see the PPT. Are you able to see the PPT?
Yes, sir, the PPT is visible.
Okay, fine. So now maybe would have done taken this at the beginning, then now then no problem. Now already we discussed some of the points which we will be discussing here. Okay, so fine. So basically we will take what is nano at this stage. So basically difference between macro, micro, nano, and what is the difference? As we already discussed, classical versus quantum mechanics. That means basically difference between macro, micro, and nano. Basically macro and micro. Macro, as we discussed in previous classes, is basically all the objects which can be observed by naked eye. Is called, we can categorize in that way, macro. So centimeter dimensions. So micro means micrometer dimensions. So basically macro and micro dimension objects are following classical mechanics. Classical mechanics. So what in previous class we discussed what is maybe classical mechanics. Classical mechanics is basically the Newtonian mechanics. So why, what is the, in what way it is a basically most important understanding of classical mechanics is that given the position given the position and velocity of a particle, we can predict its final stage after some time. That means if we know the position at t equal to 0, means at initial condition, at what is its position and what is its velocity, then we can predict where it can be after, let us say, 10 units of time or 15 units of time, 100 units of time. So that means we can predict the what's called position and velocity of the particles given the initial conditions. So that is most important point in classical mechanics. That is called Newtonian mechanics. So that means basically Newtonian mechanics will say that given the initial conditions, we can predict precisely. That's important thing. We can predict precisely the final or position or time variant positions. That is important thing. So basing on this principle, we can total Newtonian mechanics is built upon. So as you may be aware, Newton mechanics, three laws of motion and all those things, all mechanical, all engineering, all engineering what you study is basically in based on Newtonian mechanics, classical mechanics. Even you may feel that there is some quantum mechanics in micro, but basically we can understand the micro particle mechanics in with quantum mechanics, but it is not necessary. So that means classical mechanics it's also can make us understand what is microparticles and what is mechanics of the microparticles. So that means basically macro and micro, these two dimension structures can be understood by classical mechanics. What then that is what is called Newtonian mechanics. Now nano. So why, as we discussed in previous class, why nano is most important? Why nano is taking a lot of importance? Because it cannot be it cannot be understood by classical mechanics. We require quantum mechanics. So that means quantum mechanical behavior of the material comes into play when we go into nanomaterial. That's the most important thing. That's why the properties of the materials are unpredictable. There's some not so not we should not say like that. Sorry for using that word. Predictable, but it's something new than what we may expect from macro and micro particles. So by saying this thing, what I would like to say is that it is nano is not just a miniaturization aspect. It is not just a miniaturization aspect, it is more than that thing. So that means we should not think that if you take macro and micro particles and then subdivide them into nano, means then we can get nano materials. We can think of like that, but we should not be like that. Because why? Because properties of the material change drastically from micro to nano. That's what important thing to understand. Similarly, we have to see atom solid, solid to atom. So all of you may be aware that quantum mechanics started in early 1900s, means early 20th century. So around 1890s and 1900s, starting of 1900s, I think you may be aware that black body radiation. So to understand black body radiation, the first attempt of quantum mechanical understanding or something new has to be developed is known because of what is called black body radiation understanding. So with that, then people started how to understand black body radiation, and then that is the starting point of what is called requirement of new physics. At that time, new physics means classical to quantum mechanics. Okay, so that's important. I think you may be aware of that. You might have known something about what is meant by black body radiation and other things. Okay, I hope at least you might have got some small introduction to black body radiation in your 12th class or first year BTech, whatever it may be. Okay, so what it means by that, the quantum mechanics is basically is based on atom and atom structure and other things. But at that time, as I discussed in previous classes, basically people don't have experimental techniques to see to isolate an atom. But people know it was theorized that atom should be there. Minimum size of the particle is atom, and subatomic particles. All those things people are with theoretical understanding. People know. But even then, solids cannot be understood at that time. The atoms cannot be understood atom by atom because there is no experimental technique to show what is atom and all. Experimentally, it is not accessible. But theoretical point of view, people understood and people try to understand what is atom, what is the subatomic particles, what is the importance of atom. All those things people understood in theory, but not in practice. So even if we know atom, but atom understanding, experimentally understanding atom is not possible. That's why solid is being solid. Solid means what? A group of atoms. How many groups of atoms? As you may be aware, one mole of a substance will have what is called Avogadro's number of atoms. or molecules. So that means, let us say, I'm just telling for sake of understanding, then take copper. What is mole of copper? Copper mole means basically what is copper? Copper is a single element and it has atomic mass. So atomic mass grams, atomic mass expressed in grams is called atomic weight. Atomic weight or atomic mass. So that means basically that is Avogadro's number. 1 mole of a material is basically consisting of 6.023 to 10 power 23 atoms. 10 power 23 is very huge atoms. I think we cannot even imagine 10 power 23. Those many number of atoms will be there in 1 mole of the any atom, in any substance. So people try to understand the materials in terms of solids. So what it meant by that, there are 10 power 23 atoms will be there in 1 mole of the material, in 1 mole of the material. Okay, are you getting my point? Are you understanding? I hope all of you are able to listen. Okay, so that means so basically so that means basically, even though atom understanding came, but still we are comfortable in understanding what is in solid. Solid means huge number of atoms. So that means, as you may be aware, then what will happen? Band theory of solids, all those things are there. I think you are aware band theory of solids. You in first year BTech, at least you should have introduced what is meant by valence band, conduction band, band gap, and all those things. That means basically we can understand material in terms of a solid, in terms of a solid. So that means basically a solid is a material which is having huge number of atoms. So how to understand that? By in terms of band theory of solids and other things. Okay, so that means basically we will be previously we know in the solid, but now people, once we come into understanding how to make micro materials, then what will happen? Size of the material is now decreased. So let us say macro means 10 power minus 3 meters, means centimeter. Now centimeter to what is called, people came 10 power minus 6 meter, means micron. So micrometer. So even then we reduced the number of atoms from Avogadro's number 2000 times down, we can decrease. But still people felt that materials follow what is called the classical mechanics. Then what will happen? Then still at that time, I mean, few years back, maybe 30, 40 years back, 20, 30 years back, or 30, 40 years back, people still not able to understand how to make still decrease the number of atoms by going from micro to nano. But recently, or 20 years back onwards, people know how to make what's called nano materials. Then what it means is still 10 power minus 3 to 10 power minus 3 means macro, 10 power minus 6 micro, then nano, 10 power minus 9. So that means basically 1000 times still decrease. Then what will happen? Then people know now we are now decreasing the number of atoms in the solid. So now that means we are going from solid to atom. Previously atom to solid, now solid to atom. Now previously we don't understand actually atom even if we know theoretically. But now we try to understand experimentally and we try to fabricate or make materials having few number of atoms. So we are going closer to atoms, closer to atoms. Still, we don't. Nano means, as you know, one nano means what? 10 angstroms. So still, atomic dimensions are in atom. Sorry, angstroms, not in nanometers. I'm talking about atomic dimensions. So still that means we must know how to get into what's called angstrom level. But still maybe in future it will happen. But still we don't know how to make angstrom level what's called materials. But at least the nano level understanding is already there. Just few minutes. Sorry. Hello. I will talk to you later because I am in the class now. I will talk to you later. Around 12 o'clock, I will call you. Okay, so that means basically by doing from macro to micro to nano, we are going from solid to atoms or few, very small number of groups of small number of atoms. That's what important thing. Okay, in theoretical understanding, we know what is atom. Atom, as we know, you see, atoms are there. As we know, atoms basically this is a nucleus and then atomic orbitals. Sorry, electronic orbitals are there. Electronic orbitals are there. As nucleus L, K, L, M, N like that thing. So that means this is atom. So that means discrete energy levels. So atom means discrete energy levels. So this is called first K level means K atomic orbital. Sorry, electronic orbital. So it is radius is called Bohr radius, which is called A0 equal to 4 pi epsilon 0 h cross squared by mq squared. Okay, this we discuss in future means in next to next chapter. But we want to know that means basically here we want to introduce one important thing. What is that thing? Atoms as having discrete energy levels, arranged discrete energy levels around the nucleus. That's what I want to say. So okay, discrete energy levels. So that means basically discrete atoms are discrete having discrete energy levels. And first energy level, it's basically spherical shape energy levels. So Bohr radius, it is the energy level radius of the first orbital or n equal to 1 is called Bohr radius. Okay. So that what it we can say that we'll talk it later. But what I want to say is that from once we go from atoms to solid, we are going from discrete energy levels to bands. Okay, so now you see K, L, M, N, then band gap, then valence band, conduction band. So that means basically what is happening from atoms to solids. Atoms are basically the discrete energy levels, solids exhibit what is called band structures. Band structures. So this is important thing. So whenever band structure comes into place, we are talking about a solid. Solid, okay. That why? Because as you may be aware, that bands, how band energy bands will happen, energy level bands will happen when more than when more number of atoms are coming together, coming closer to each other, rather one another, then what will happen? All corresponding energy levels of each atom will constructively interfere and form what is called band of that particular discrete energy level. So what it means by that, K what's called discrete energy level forms K band. L discrete energy level will form L band, M band, N band like that thing. Then very close to well, we once we come to Fermi level. Hello. Tell me, madam. See, I will send you, madam. I'm somewhat busy. Maybe I will talk to you in the evening. Hello. Please tell me, madam. And sorry for disturbance. So I got one phone call. That's why I stopped. Sorry for disturbance. I hope you are listening to me. Okay. Okay. Now that means what I'm trying to convey to you is that we are coming from going from atoms to solid, then corresponding discrete energy levels are transformed from discrete energy level to the band. Now what we are doing in nanoscience, then solid to atom. So how can we, what we can expect? We can expect that when as number of atoms are decreasing in a nano material, then what we can expect? We can expect now first and foremost the bandwidth. Let us talk about valence band, because that is generally we discuss. So valence band width will decrease as we are reducing the number of atoms. Then as we are going from, let us say, 1 nanometer or 2 nanometer, like that, what we can think, then we are now going to towards discrete energy level situation, from band to discrete energy level situation, from band of energies to the discrete energy level situation. So then from solid to atoms we are going. So when we are decreasing the size of the material or material particle, then we are going from solid to atoms. Then in consequently the in the energy diagram, in the K space, the bandwidth, let's say valence band width will decrease such that we are coming closer to atom, and once we come to atomic dimensions, then we can have what is called discrete energy levels. So that means, what it means by that, nano, we can think of nano science and technology to coming from what is called quantum mechanical range. So from solid to atoms, as all of us know, atoms or group, a small number of group of atoms will follow quantum mechanics. So that means we are coming from solid to atoms, from classical mechanics to quantum mechanics. I hope you get my point. Okay, so now just for sake of understanding, next class or next chapter we will discuss length scales. In that length scales, we will have what is called Bohr radius, which is A0 is equal to 4 pi epsilon 0 h cross square by m2 square. What is then radius of the first orbit, and epsilon 0 h cross m, all those things are there here. Okay, we'll discuss what is Bohr radius in the coming chapter. Okay, so now at this stage, once more, please don't mind if I say once more that we are nanoscience means we are coming from solid to atoms. Then from energy bands to discrete energy levels. From classical mechanics to quantum mechanics. Okay, so this is important thing. Once we know that we are approaching quantum mechanics from going to micro to nano, then we can definitely expect a great number of material properties, and then definitely the material properties will definitely drastically different from micro to nano. That is the important thing. That is the beauty of nanomaterials. It is not just decreasing the size of the particle. It is more than that. We are now trying to access quantum mechanics. We are now trying to access different exotic properties of the materials. Okay, that's an important requirement of that. Okay, so that means solid. You see, solid means number of atoms in Avogadro number, n equal to Avogadro number is 6.023 10 power 23 per mole. So that means metal electron density is basically what we can say is that 8.9 to 10 power 28 electrons per meter cube. That means basically in a solid, these many number of electrons will be there. 8.9 to 10 power 28 electrons. This is metal. This is metal. So all of you know metals conduction band electrons C. highest number of electrons will be there in the conduction band of metal. What is that highest number? 8.9 to 10 power 28 electrons per meter cube. For semiconductor, as you know, it is not as high as metal, but it is 1.5 to 10 power 16. Okay, electrons per meter cube at 300 Kelvin. Okay, then for pure germanium, it is 2.5 10 power 10 power 19 per meter cube at 300 K. So that means basically I want to tell to you by giving this these numbers, what is Avogadro's number and what is the electron density of metals. It is 8.9 to 10 power 28 electrons per meter cube. What is electron density of semiconductor? And generally, it is 1.5 10 power 16 per meter cube at 300 Kelvin, or pure germanium, for pure germanium 2.5 10 power 19 per meter cube. Okay, so I hope you understand why we didn't give at what temperature for metals, what is the temperature, the N electron density. Why? Because since it is 10 power 28, so it is a huge number. So temperature doesn't have any effect or considerable effect in increasing or decreasing the number electron density in metals. But in semiconductor, as you must be knowing in semiconductors, temperature has very great importance, because at what temperature we are considering the material. At 300 Kelvin, this is the density, electron density, this is called intrinsic electron density for pure silicon. Okay, so pure germanium 2.5 to the power 19 per meter cube. Oh, I hope you understand why temperature effect. Once we increase the temperature, electron hole pairs will increase. All those things will happen. Then because of that effect, then the number of electron density can be increasing. That's why we have, whenever we are talking about semiconductor electron density, we have to mention at what temperature we are talking. Okay, for pure silicon, what it means by pure silicon? I think you understand what it means by pure silicon. Why I put pure silicon? Because it's intrinsic material. I hope all of you are aware of that concept. Okay, so I hope I need not get more into that. Okay, now nanostructures basically transmission electron cadmium selenide quantum dots. Okay, already we discussed this aspect. Now what we are taking, see, size dependent optical emissions spectra. This is mercuric sulfide. This is mercuric sulfide and this is cadmium sulfide. Now you see one important thing: smaller quantum dots emit or absorb blue or green. So smaller, see, you must understand one important thing. So larger ones, red will come, red emission. Smaller ones, blue or green. So you see, smaller ones basically these are the smaller ones. This is larger quantum dots. So basically, red emission is there. Means we are seeing the quantum dots as red. Okay, is it not? So that means basically what I want to say is that here by showing this material, basically what it is, optical properties, optical emission is optical property. So optical property of the materials will change with what's called size of the quantum dots. So what is quantum dot? We will see, come to know. Okay, you understand what I'm telling? So quantum dots means quantum material. Yeah, when it is a small quantum material, quantum dot material, it is having emission of in blue or green, but in higher larger dimension, it is emitting red. So what means optical property, optical emission property will change with size. Okay, why? Because as already just small way we discussed, that means discrete energy levels will be there, all those things. Now you know graphene and all those things. We will discuss these things in coming few classes. And then we have what is meant by metal nano rods. See, you see metal nano rods are there. Okay. Now TEM of palladium, PD means palladium nano rods. So these are all, are you seeing? Huh? I hope you understand what I'm trying to say. So there are, since they are, it is showing like a line, but they are rods because they are in the dimensions of nano dimensions. Just this is just a schematic, but this is all, these are all actual quantum. I mean, sorry, palladium nanorods means the radius of the nanorods will be in the range of nanometers. That's why it's called material is palladium, so palladium nanorods. OK, so already we discussed what is meant by periodic lattice and then polycrystalline, crystalline, and all these things we discussed. So now I want to see one more thing. Hello, 1 minute. Are you understanding what I am trying to explain? Aryaman Banerjee?
Yes, sir.
No confusion?
No, sir.
OK. Kanya Singh, are you able to understand what I am trying to say?
Yes, sir, no doubt.
OK, so please, if you have any doubts or if you have any doubts or if you feel I am going fast, please let me know. You can talk in between, no problem for me. OK. OK, now this view graph is done. I will put up some other thing here. These things we already studied just now. This we have studied. So now I want to show here. What is when, see, I think all of you are seeing this, and this is a textbook. I will upload to, I don't know whether I uploaded, I will upload today such that you people can read this thing. OK, so now important thing is that why nanomaterials follow quantum mechanics? In what way we can understand quantum mechanical behavior comes into picture? So we have to discuss about what is called low dimensional systems, low dimensional materials. What do you mean by low dimensional? So all of us know that we have in real world we see three-dimensional objects. So whatever we see in the real world is a three-dimensional object. So that means what is meant by three-dimensional object? It has the material which we are seeing or object we are seeing is having length, breadth, and width. So certain length, certain width, certain breadth will be there. So that means it has all three dimensions. It has what's called it spreads. It means the material which we are discussing in the macro scale or in real world. So that's why it is called three-dimensional material, three-dimensional structure. What is meant by that? Already we discussed one important thing. What is that? Crystalline structure. What do you mean by crystalline structure? The material in which atoms are arranged in regular fashion in all three XYZ directions. So at that time we are discussing three-dimensional object. Hello, are you able to see? Are you able to see? Hello?
No, sir.
Are you not able to see the now what I put?
No, sir.
OK, I will see that one. Just OK, I might have done wrong thing. Okay. Now are you able to see?
Yes, sir.
OK, OK. Thank you for giving input to me. Fine, it's good. So now that means what I did is that previously stopped presenting before loading this. That's why it happened like that. Anyway, thank you for giving me input. Okay, now that means what it means. We know in real world three-dimensional objects. So that means the atoms are arranged that not necessarily in the crystalline structure, whether in crystalline structure or in amorphous structure or in polycrystalline structure. All these normal materials which we see are having what's called X, Y, Z directions. Their materials are in all X, Y, Z directions. So that's why they are called three-dimensional structures. What it meant by that? Now already we discussed one important thing. Since atoms are arranged in three dimensions, since each atom has having outermost energy electron, those orbitals of outermost energy electron are overlapping to one another. Then outermost energy electron is now able to move in all three dimensions, X, Y, Z dimensions. Are you getting my point? In three-dimensional structure, in three-dimensional object, in three-dimensional material, we must understand one thing. Electron, outermost energy level electron is able to move in all three dimensions, X, Y, Z dimensions, but not in Cartesian coordinates. Once we talk about electron, we have to talk about what's called momentum space. Positional momentum space, X, P, X, X, Y, P, Y, Z, P, Z. Momentum, it's called momentum space, not in Cartesian X, Y, Z directions, but in just like in Cartesian X, Y, Z directions, in momentum space also, we have X, Y, Z three-dimensional system. So that means basically the electron is able to move in a macroscopic material. Electron is able to move in all X, Y, Z directions. In the momentum space, try to understand. Let us not, whenever we are talking about electron movement, we have to understand it is happening not in Cartesian coordinates, but in momentum space. Means Px, Py, Pz means X, Y, Z directions are having P. P means momentum. Momentum, X direction momentum, Y direction momentum, Z direction momentum. So in momentum space, it's called momentum space. In Cartesian coordinates, it's called configuration space. I think you may be aware of this thing. So now, whenever we are talking about energy of electrons and other things, we have to talk about in momentum space. Okay, I hope you understand this point. So now that means electrons move freely in all three Px, Py, Pz directions whenever we consider them in a what is called macroscopic object, three-dimensional object. So let us think we are decreasing the one of the three dimensions such that the electron is unable to move in that direction. What is meant by that? So all of you may be sitting in your rooms, in your rooms, and room, as you know, is a three-dimensional object. So that means X, Y, Z directions are there to wherever you are sitting. Think about in that room, roof of the room where you are sitting is progressively coming down to the towards the earth. Okay, then what is happening? Then let us think one thing. For sake of understanding, try to what's called stand up. Then, depending on your height, when the roof is coming down up to certain distance, then depending on your height, you can move on the plane of in the ground, depending freely or not freely. When the roof is where it was, then you can jump. Means you can go Z direction also. You can access Z direction. And you can access X and Y directions. But once the roof is coming down, depending on your height, You cannot, your movement in the z direction is restricted. You can't just move in the z direction. You cannot just jump. After certain height, the certain distance, the roof is lowered, depending on your height. So what is meant by that? You can still, even at that condition, still you can move on the ground of the room, but you cannot jump. That means your motion is restricted in the z direction. Now replace yourself with electron. So that means what is happening? Electron, in normal circumstances, electron can move in all XYZ directions. But in when the height of the what's called z direction material, z direction is thin, no material is there in the z direction, or minimum width thickness is there, then what will happen? Electron cannot move in the z direction as freely as it was. Slowly and slowly, it means electron's movement is restricted in the z direction, but still it can move freely in x and y direction. I hope you are getting my point. Then what will happen? What is the proper? So that means electron can move from in x and y direction freely, but in z direction it cannot move because of the dimensionality control. Means now thickness, means z direction thickness we are reducing. Material thickness we are reducing. OK, I hope you are getting my point. Then we decrease in such a way that electron cannot just move in z direction. That means thickness of the material in z direction is coming what's called in nanometer range. Means height of the material or thickness of the material is in the few nanometers. Then electron, depending on the material, electron cannot move in z direction, but electron can move in x and y direction. So that means electron can, what is meant free means, what is meant by free? Electrons can access all continuous energy levels, continuous values of energy levels in XY directions, but it cannot access the energy levels, continuous energy levels in the z direction because it cannot move, it is restricted. Then what will happen in XY direction? It can move freely, but in Z direction, it can move only discrete energy levels only. It means electron can move. It cannot move. It cannot assume or take continuous energy levels, values of continuous energy in the Z direction, but only what's called quantized energy states only it can access. So what is meant by that? Now electron movement in the z direction is quantized. In the that direction. So that means basically electron cannot move freely, but only in discrete energy levels in that direction. However, in x and y direction, the electrons can move freely. That means it can take continuous energy. It can take continuous energy levels. OK, I hope you got my point. If you have any doubt, please let me know. If you have any doubts, please let me know. Because I saw I'm teaching this subject for last 1 or 2 years. Then I'm seeing whenever a question comes, what is meant by quantum structures or low dimensional structures, people will not give the proper explanation because they don't understand it. So if you really understand, you should be able to know how to write properly, how to understand and put your views properly, what is meant by quantum aspects, in what is meant by low dimensional systems or low dimensional structure. Why it is called low? Because now electron is moving in x and y direction, which is called two dimension, but in that direction it is restricted. That's why it's called, this type of system is called two-dimensional system. Three dimension to two dimension means low dimension. Okay, are you understanding my point? So that means basically, then what is the physical material form of the two dimension? Thin films. Thin films. Okay, thin films in which the electron cannot move in that direction is called two-dimensional structure. One more thing also is there. What is that thing? There is a, please see here, there are two blocks, in between there is a gap. So that means one below one block is there, upper one block is there, below there is a gap. So that means basically what there is, let us say, I'm just thinking there is one material in the lower block and that material in the upper block, but some other material in the middle block. So now electron of the middle block cannot cannot go into upper block or a lower block. What may be lower block? Lower material or upper material? Because the upper material has having what is called the continuous energy levels. Electrons will take continuous because it's a macroscopic thing and this is also macroscopic. But in between there is a material which is very thin. So that's why it's called quantum well. Quantum well, two-dimensional quantum well. Okay, do you understand what I'm trying to say? This is all two-dimensional quantum well. So this is also two-dimensional, but it's called quantum well. Why it is quantum well? People call that there is the quantum structure in between two what's the other materials wherein all three z direction possibilities there. Okay, this is macroscopic, this is macroscopic, but this is nanoscopic. Okay, that's why electron of the material, quantum well material, cannot go into upper material or lower material. Now it is confined. It is confined in the XY what's called space of the middle material. That's why it is called quantum well structure. Why it is called quantum? Why it is called quantum? Because its behavior is quantized in z direction. In z direction, not in xy direction, but only in z direction. Since electron can move in x and y, means 2 x is 1 to y is equal to 2 means 2 dimensions, but not in third dimension. That's why it is called two-dimensional quantum well. Okay, so do you understand what I'm telling? Do you have any doubts? Do you have any doubts? Okay, since nobody is giving any indication of any doubts, I suppose that you people are understanding. So now that means basically it is called two-dimensional structure. Two-dimensional structure can be just a thin film on a substrate or a thin film bounded by two macroscopic materials, macroscopic or macroscopic or microscopic materials, such that the electron from the middle material will be restricted in that direction. Okay, that is also, it is called quantum well, two-dimensional quantum well. Now after that, so that means basically electron is now restricted in the z direction. In the z direction. So in that means other than xy direction, it is restricted in it cannot go in that direction. Now if I try to say that electron cannot move both in z and y direction, only it can move x direction, then what will happen? Only in one dimension electron can move. What is meant by that? Take the example as we discussed as a room thing. Now roof is progressively lowering and one of the walls is also moving towards another wall, means parallel wall. Then what will happen? Both the person, think about yourself. Now you cannot move in y direction. Only in x direction you can move. In z direction also you cannot move. That means both in y and z direction you are restricted. Similarly, in two dimensions, previously in two-dimensional structure, in two-dimensional electron is moving. Now two-dimensional electron is unable to move. It is restricted. Or get my point? So that means the electron can move only freely only in one direction. Other two directions it cannot move freely. That means it cannot move freely means it cannot take continuous energy levels. It cannot occupy continuous energy levels. It can occupy only quantized discrete energy levels. Okay, in the direction which is wherein it is restricted. So that means since it means electron is now moving only in one dimension freely, means let us say x direction. Both y and z direction it is unable to move freely. Then this type of structure is called one-dimensional structure. One-dimensional structure means only in one dimension, whether it can be x, y, or z, because x, y, z is only a naming, nothing very important. That is only a name. So it can either be in one x, y, or z. But we take for sake of understanding in x direction the electron is moving freely, but in y and z direction electron is restricted. Electron movement is restricted. Means electron energy levels are quantized in y and z direction. So electron can take can freely move in the x direction, means it can assume or it can take continuous energy levels in x direction only. In y and z direction, the quantized energy states are there. That means electron can take only discrete energy levels. Okay, so this type of what is called material is called one-dimensional structure. What is example for this thing? Just now in previous PPT you saw. What is that called? Nano rods or nano wires. Nano rods or nano wires, or a system in which atoms are arranged in a line of atoms. All these things are called one-dimensional structure. Now that means now in this two dimension, electron can move in two dimensions. In one dimension, only electron can move in one dimension. Then naturally we can think of possibility of other possibility. What is that? Electron cannot move in all three dimensions. It can be localized. It cannot move in x, y, or z direction. It can be localized. It means electron. Electron can be localized in certain volume. Then it's called quantum dot. Quantum dot, or this is also called artificial atoms. Now electron in this case is restricted in all three dimensions, x, y, and z direction. Electron is now restricted x, y, z direction. It cannot take any continuous energy levels either in x, y, and z direction. It is now localized. It doesn't have any what is called movement. Only in certain volume it can move. Certain volume. Other than that, it cannot move. So that means in this case, the electron has no continuous energy levels in either x, y, or z direction, but it can assume or it can take what is called the quantized energy states in all x, y, z directions. So that's why it is called quantum dot, DOT dot, quantum dot. Electrons can move only in certain volume of the quantum dot. In all three dimensions, the electron energy levels are quantized. So two-dimensional structure, one-dimensional structure, and zero-dimensional structure. Now these things are called low-dimensional structures. Basically, all quantum mechanics will have either of these three, any of these three structures. Either it can have quantum well, or quantum dot, or nano two-dimensional nano, or two-dimensional one-dimensional nano, or quantum dot. One more thing also I will tell. What is when the actual quantum means in all directions. This is actual. That's why I'm calling this quantum dot. I'm not saying quantum wire or quantum two-dimensional structure. Why? Why? Because basically the now depending on the size of the wire means rod, it can either restrict in all three dimensions, in x and y directions completely, but it can have, but only in quantum dots it will be, it means electron will have quantized levels in all three dimensions. Okay, I hope you are getting my point. Okay, if you have any doubts, please let me know. Because you may think that you are understanding, but what with experience I can tell, you may be feeling you are understanding, but while you are writing, how to write something, people are not expressing things properly. That means they don't understand or they don't read, whatever it may be. Both are same. Vedant, Srikanth? Vedant? What happened?
Yes, sir.
Any doubts?
No, sir.
Shura? Ayush?
Yes, sir.
No doubts?
Sir, for today's class, sir, not very clear. I'll watch the recording again, sir.
Okay, please do that. Otherwise, Drishti?
Yes, sir. No doubt, sir.
Okay. Manik, Gana, Manik? Manik? Please respond. Aryan? Jayesh Aryan? Okay, so I will take it as you are understanding. Okay, because some people are told they understand, some other people are not responding. So I will take it as a yes, means you are understanding. So what it means now, why they are very much important, as I have told, basically low dimensional structures are very, very important. All quantum mechanics is basically dependent on these type of structures. So quantum mechanics or nanostructures are basically making any of these three type of structures, whether quantum wells or what's called two-dimensional structures or one-dimensional structure or quantum dots. Either any of these three we require to prepare, because then only the material behaves according to the quantum mechanical rules. Otherwise, it is basically a micro at best it's a micro material which doesn't have any quantum mechanical behavior. Okay, I hope I understand now these things. It's very, very, very important to understand what is meant by low dimensional system. See, okay, I don't go into because these things are not necessary for you. I have shown, I think, this TM. You see, one important thing: transmission electron microscopy, which we will be discussing in a coming few classes, is most important. What's called technique, wherein we can have what's called crystal structure, because basically it is a transmission electron microscopy, means it's a crystal structure aspect. You see here quantum CDSC means cadmium selenide. See, it's a quantum selenide, sorry, cadmium selenide quantum dots. Each these black spots are cadmium selenide quantum dots. Okay. Okay, so that's what it is. Now you can see last time we discussed one important thing. What is that? In X-ray diffraction we discussed. What is that X-ray diffraction? Once you take a periodic crystal, whether it's a three-dimensional periodic crystal or two-dimensional periodic crystal, then if you do that's called a diffraction experiment. See, in that at that time we discussed about what is called X-ray diffraction. See, any not necessarily X-ray, electron diffraction is there. I think you may be aware. Why X-ray electron diffraction? As you know, electron is a wave. So that diffraction is a property of the wave. Property of the wave. So that means any wave, any type of wave will diffract, will interfere, will polarize. So these are fundamental properties of waves: polarization, diffraction, interference, diffraction, polarization are fundamental properties of waves. Any type of wave, whether it's a electron wave or what is called optical wave or a matter wave. I hope you understand what is meant by matter wave. So all these waves will have all these three properties. So by utilizing electron wave to understand the crystal structure of this type of material, we can have electron diffraction. So you can see, but principle is same. The way we do is different. So this is a what's called central beam intensity. Now you see there is a dots. There are dots which are what's called having what is called arranged in a regular fashion. So this shows that means basically the crystal is periodic crystal. We can see this is a periodic crystal, and with the electron diffraction also we can see the what is called the structure is periodic. So that means transmission electron microscopy is most important technique to understand crystal structure of what's called materials. Okay. I'm sorry. Sorry.
I will join at 2:15 if we start.
Ah.
At 2 afternoon.
Okay.
I'll join at 2:15.
Okay. Okay, so that's what it is. Okay, so that means basically we can see very clearly that crystal is a periodic crystal, and we will get corresponding electron diffraction result. This is a as we discussed in previous class. This is a direct beam intensity, and these are all intensities of diffraction pattern. This thing. Okay. Okay, so this is what I want to say about why it is nano. What is nano? Okay, now in next class we want to discuss what is called now what is meant by. Okay, what we discussed two important things. What we discussed is basically the crystal structure, because as I told discussed some time back, crystal structure is most important because it will determine the structure wise properties of the materials. Structure means crystal structure is important. It will determine how electron wave functions will overlap with one another and thereby giving properties of the materials. So crystal structure is very important thing. Okay, so we discussed very briefly and some fundamental points. We should not claim we know many things because it's the first course. That's why we discussed only that much. So that means we know what is meant by lattice, we know what is meant by crystal structure and all those things. So then afterwards, now today we discussed what is why nano, what is meant by nano. Okay, now that means we discussed low dimensional structures. What is maybe low dimensional structures? What type of low dimensional structures are present, and what 2 dimension, 1 dimension, 0 dimension, and in what way they are important, in what way they exhibit quantum mechanical properties. We discussed that thing. Then many things are there in this thing, but we don't go much in this chapter because it's an introductory chapter to this particular book. That's why they are giving a lot of other things which we won't discuss. because most important thing is to see the transmit TEM picture, TEM micrograph of the pre-reactor crystal, and the electron TEM means electron diffraction, what's called characterization of two-dimensional crystal, and most importantly, and then we discussed what is meant by low dimensional structure. We discussed, and then I have displayed some optical properties of quantum dots and other things. Okay, now in the next thing, what we have to discuss? The next thing what we have to discuss is length scales. So what is meant by length scales? Length scale means, now I will ask you one question. What is that thing? How much is what is the dimension of nanoparticle to call it as a nanoparticle? Okay, so now we discussed one important thing here. What we discussed? Nanoparticle should become low dimensional system, whether it's a two-dimensional, or one-dimensional, or zero-dimensional. Nanoparticle is a low-dimensional system, whether it can be two-dimension, one-dimension, or zero-dimension. Why? Because nanoparticle is inherently low-dimensional system exhibiting what is called quantum mechanical behavior. Okay, now quantum mechanical behavior. So now what is meant by that? So depending on the material and depending on the property of the material, we have to define what is actually nanomaterial. For some material or some type of experiment, the length or dimension of the particle, let's say, I'm just for sake of understanding I'm talking. What is that thing? Some 50 nanometer particle can be called as a nanoparticle. For some other property or some other material, 50 nanometer particle may not be nanomaterial. Why? What is criteria for that? Important thing is that what is criteria? Criteria is it should exhibit at least in one dimension. Out of 3 dimension, at least in one dimension, it should exhibit what is that? Quantum mechanical behavior. So depending on the material, depending on what is the property of the material we are discussing, we have to define what is called nanomaterial, nano length scale. So what is that length scale by which you can identify nanoparticle which will exhibit quantum properties, at least in one dimension? May not be in all 3 dimensions. Okay, that is called length scale. Length scale. Okay, now that means basically, so that's what we want to discuss. Again, one thing more I will tell you. When we are discussing what is called, when we are discussing the conductivity property of the material. What will be conductivity of the material? Electron conductivity means how electrical conductivity. Electrical conductivity means what? When we put voltage across a material, electrons are moving, thereby giving some current, or vice versa. If you put voltage, current will give. If you put current, voltage will come, as you know better. So that means electron is moving. So electron is moving. When electron is moving, talk about metals. Talk about metals. When electron is moving in metals, electron SESC. Just now we discussed 10 power 28. Number of electrons will be there for one meter cube volume. A huge number, which we cannot even imagine. So that's why it is called electron C. So when electron is moving, naturally electron will collide with another electron or one more electron. Is it not? So that means basically electron collision is an important what's called property for electron conductivity aspect. So that means electron collisions will limit the electrical conductivity of the material. Is it not? So that means what is the property by which we can characterize the electron collisions, as you may be knowing? Are you aware of that? What is the parameter? The electrical conductivity of a material is dependent on. Any one of you are aware of it? Tanya Singh? Tanya Singh?
The concentration of or the ions in the material.
No, now we are not talking about atoms or materials. Sorry, ions. We are talking about electrons. So what it means by that, as I just now told, electrical conductivity means what? Electron is moving from one place to another place. It is actually moving, or wave is moving, wave propagation is taking place. So what is meant by that? Electron collision is taking place. That is the restricting parameter for getting more electrical conductivity. So how can we characterize electron collision? By what is called lambda, which is called distance between two collisions, successive collision. What is that thing? Distance traveled by electron between two successive collisions is called mean free path. So mean free path is an important parameter which will determine the conductivity of the material. Why? Because mean free path will tell us what is the length before electron collides with another electron. So electron can travel, for sake of understanding, I'm telling 10 micron, let us say 100 angstroms before it can collide with another one more electron. So conductivity of that material is minimum distance traveled by that material. Is it not? That electron. So what it means, what I'm trying to convey to you is that the mean free path is an important parameter by which we can characterize the conductivity of the material. So now we can think the nanomaterial for conductivity purpose can be characterized by lambda. Lambda means mean free path. So that means when the thickness or dimension of nanoparticle or nano thin film is less than or equal to mean free path, then we can call that as a thin film or two-dimensional thin film. Do you understand what I'm trying to say? Are you able to understand what I'm trying to convey? Hello? Aryaman Banerjee?
Yes, sir. Got it, sir.
No problem?
No, sir.
Jayesh or Aryan? Jayesh Aryan? Shruti Sandeep?
Yes, sir.
Please are you able to understand? Did you get what I'm trying to explain now?
Yes, sir. Mostly, I joined a little late because I had a placement test for another for a company today. So, but after that, I have understood most of it.
Okay, fine. So that means, so what I'm trying to say is that now that means the dimension of the nanostructure, whether two-dimensional, one-dimensional, zero-dimensional, for a metal, for conductivity purpose, depends on the lambda. Lambda means mean free path. When the dimension of the particle, whether it's a thin film or a one-dimensional or zero-dimensional thing, is less than or equal to lambda, then we can call this as a nanomaterial of that dimension. So that means we have to discuss, we have to define the nanomaterial for a particular property What is the dimension of that for that particular material? Okay, so that's called length scale. At what length of a particular for a particular material for a particular property, the material behaves like a quantum aspect, quantum behavior, will exhibit quantum behavior. That is called length scale. That we will discuss in the next class. Okay, so we want to discuss the semiconductors because now semiconductors, what is the dimension of semiconductors wherein we can have, in semiconductors, there are two types of charge carriers, electrons and holes. So that means basically the at what dimensions of the semiconductor nanoparticle, okay, will have confinement in all three dimensions for optical property. That's what we discuss in the next class. Okay, so please be there. I'm taking now. I want to. It's already 11:55 or so. So I want to stop today's discussion and then please be there. I will be taking what's called the attendance. Okay, I took attendance. Now, if you don't have any what's called queries, you can log off. If you don't have any queries or if you have don't have any questions to ask or doubts, you can log off. Okay, I'm now leaving the class. Class is over, so I hope all of you are leaving.